this sound still haunts me to this day.
Oh, yourself. Uh-oh.
I still remember playing Serious Sam on the couch with a small TV screen, especially in co-op. Really, really fun times. Serious Sam is a fun game. At least I remember it like that. But even though the enemies are pretty stupid and just run straight to the player, it's still entertaining. It's not very algorithmic, but it's entertaining. Now for your game, you might not want such basic behavior of enemies just running straight to the player and then agglomerating into this mess of a huge triangle ball just trying to all hit the player at the same time. The issue is that, the enemies don't respect each other's spaces and they are not coherent in their behavior as a group of enemies. They are basically just zombies all trying to pack each other on this target destination that you gave it to them. So today we're talking about how can you improve the positioning of your enemies? Because at the core, you have the navigational system, but you need a smarter way to position your enemies at certain places around the player to attack then the player. So this is what we're going to cover today. So there's this article, Implementing Robust AI for Secondhand Enemy Positioning. It's from 2017, but still fine. So Secondhand, I think, is the name of the game that this person develops. Has heavy emphasis on melee combat. For the enemies to be challenged and dangerous, they need to be able to reach a position where they can attack. So typical melee combat, you don't want to just all the enemies run to you and then try to hit you. They need to kind of position themselves in a smart way to hit you. So this is especially challenging given the twin stick nature of the game combined with high physicality. The problem is compounded by the high number of enemies and the multiplayer aspect. Okay, probably we're not going to talk about multiplayer here, but let's focus on the rest. Simply put, the problem we're trying to solve, what is the best position for an enemy agent to be at any time? And that's a great summary. So you have the navigational system. It allows you to tell the enemy, you can go there, and the enemy will just find the best path to go there. And sometimes that's not always what you want. For example, the navigational system finds the shortest path. So he might be cases where the enemy is really like going very close to walls and so on, when you want it maybe to be more natural. So there's a lot of work to make the enemy feel natural. And the second part is, what is the actual destination of the enemy? So if your player is at point A, actually your enemy's destination is not really point A. It is a point where whatever the enemy wants to do is the optimal position for doing that action. So if it is an melee attack, okay, the enemy must come pretty close to you so it can hit you. But if it is, for example, an archer or someone that is has any kind of ranged weapons, well, it's not really the best position to go as close as possible to the player. It might be, oh, maybe I should climb up to that tower and shoot the player from there, and this kind of stuff. So we have an AI system that we need to decide what is the best position for your enemies. So let's move on. Different enemies have different preferred locations depending on range and personality. Yeah, some prefer to flank, others prefer to attack head-on. That's also a great way to put it. Lots of enemies, agents at the same time. Varied environments, multiple targets, chaotic and physical combat. Needs to be easy to set up. Yeah, we can also leave this out. So here's a great three-step solution, and I think this explains better. So the first step is, this is a target, we want to attack him, this is the enemy. Where will the enemy position itself? So we can compute, let's say, a few circles or a few positions in a circle around the target. Then second step would be to give a score to each position. So based on, I would assume, let's say, the characteristic of the enemy and the characteristic of the environment, some position would be like, okay, this is the best position, this is the less ideal position, this is even a worse position, and maybe some position you say, well, those are no-go positions because there's a wall or something that blocks it. Or it's already being taken, maybe an enemy is already there. So that's the second step, and then the third step is the enemy picks a location, and this is his location assigned for some time. So this is how you would go about it, step by step. And I find this article really great, so I will link it in the description so you can read it at the end as well. So you have your player and you just compute your positions and sample them all around him. So here is kind of a circular pattern, but of course you can do any kind of pattern that you want. Maybe each enemy has its own pattern and so on. So here is just a radial position generator that is generating this. So you can already see where we are going. Some dots go under the environment, some dots go behind covering a kind of a cover, and so there's some filtering and scoring to be done now. So he starts off by actually filtering or deciding which position would be valid or not valid. So let's build a filter that takes a point that does a nav mesh line of sight check. Okay, towards the center. No use going to that position if the enemy can't see the player. Yes. So he takes a point, makes a line of sight from the point to the player, and if there is no line of sight, then it's not a valid position for a melee combat. It might be for a range combat. Imagine someone is behind that wall here, and this enemy has, a grenade launcher to throw a grenade above the wall. That would be then a valid position for that enemy, but not for a melee enemy. All right, pretty easy for now. Sample scoring. Okay, I'm assuming there are many ways to compute the scoring. So let's see what has been done here. So everything is enemy centric from this point. Each enemy agent will have its own scoring stack and parameters. For those worrying about performance, I'll talk about that later. Each position needs to be evaluated and given a score, and we want the scoring to be parametric. This is why we create multiple scoring stages that we can stack and form a final score. Okay, so we have a stack of scores. Okay. So the process looks like this. Position payload, scoring stage, we calculate, stage result, normalization, stage result, modulator, score result. Okay. So let's see what let's see what each of those are doing. In the diagram above, construct scoring stages that have a score calculator. So the score calculator evaluates and scores a position, and a modulator modulates normalized scores. We feed in positions, score them, normalize the score into 0 and 1, and then apply things like fall off, inversion, and weight. And you can follow the flow of the data based on the numbers of the numbered stars. Does it go through 1, 2, 3 or not? Because it's like 1, 2, 3. We feed the positions, okay, score them, right? Normalize the scores into a range of 0 and 1. So here's the normalization right here. Okay, and the modulator are the effects like fall off, inversion, weight, and so on. So those are the modulators. That's a pretty nice structure. You can imagine in terms of classes how you would organize that, and it would be pretty modular to work with. So what's a payload, you might be asking? The payload contains data needed by the calculators, such as the position of the other enemies or the parent of the position being evaluated. The position itself is contained in the payload, but for the sake of clarity, the diagram shows it as separate. Yeah, that's true. So the payload would be basically like the blackboard of your game. Everything that the enemy must, or actually yes, this system must know everything that is happening in the game to be able to use any kind of variable or parameter existing to take the best decision. Because maybe there are additional things you want to take into account. Maybe you want to, if there's a fire here, it is becoming not a valid position for enemy A, but maybe for enemy B that has fire resistance, it is a good position. This kind of stuff. So yeah, having a flexible payload and then the calculator or the stack of calculators uses what they need to do their computation. Probably, when you start out building a system like that, you would have something very simple where the calculator and modulator and everything is just in one place. And then as you move on and create a more complex system and you have more enemies, maybe you will start splitting each calculator into its own class, each modulator, and so on. So after the scoring, So whatever the scoring is, the enemy have preference distances to this target. A parametric distance stage result would look like this. Okay, so let's say the melee enemy says, I need to be as close as possible to the player. Well, then it makes sense. The most closest are green, and then it becomes the score decreases based on the distance. So if there would be no place, if every object would be having already an enemy assigned, then the enemy, even if he says, okay, I need to be really, really close, but there's no other place left, then whatever, he takes whatever is left, even if it is on the outside. And from there on, it's like, it can go more and more complex. Maybe the enemy says, oh, I would like to come closer. And the other enemy that is close says, actually, I would at this time want to swap my position with someone else because maybe my health is low or something like that. So those are like not that complex rules, but they can create kind of an emerging feeling of a really advanced enemy. But this is something you implement step by step, as it is shown here, basically. So if the function is parametric, it becomes reusable and a very good tool in creating personality with the same building blocks. Yes, so he thinks in modularity from the beginning. That's good, I guess. So here he changes the preferred distance to have different results. So let's say if the preferred distance is more far away, then you get this other visual representation here. So maybe range me prefer this one, other one there. So that's a great way to see. That's already great results. Performance-wise, let's see what he's doing at the end. Because those are a lot of points. If you need to compute each of those points every frame, that's a lot. The modulation at work. So one modulation would be inverse. The power function, So all those things, the calculator and the modulation, basically makes your system more modular. So here's another example with dot product between A, enemy position, and B, the target position. We're telling the enemy that he prefers points between the player and himself. And we're messing with the power exponent to create a wider or narrower cone. That's really a great visualization and use case for the dot product. And it's not that complicated. It's really a good example. So you could imagine where some enemies prefer to backstab the player and some enemies prefer to come in the front with their shield or something like this. So now he has both. So he checks which points even qualify to be in the scoring system, and then he scores them. And the qualify one is probably really a good way to start with that, because then you save all the computation for the rest. So here you have an example with an enemy. It looks great. Looks really great. So let's try a fun one. We don't want the enemies to get trapped in corners. We want them to stay away from walls. Let's create a stage that scores point distance to the edge of the nav mesh. Oh, that's great. So everything that is too close to a wall gets a bad score, and the enemy avoids that position. That's really cool. That's a really great way to make the enemy kind of feel aware that he cannot fight a melee combat with a wall behind your back. That's really interesting. Multi-agent problem. Okay, so with this already, it's good work. We can go and continue. We are ready to tackle the problem of multiple enemies competing for positions. When adding two enemies, it's very much imaginable that they can choose the same point. How do we prevent that? So maybe you have already an idea. I'll let you think. First idea, score the distance to other enemies and invert the result. This will cause the point close to others to have a lower score and the best points to be the ones farther away. This doesn't work well in practice because everyone is moving and influencing everyone else. Yeah, that was what I was thinking when reading this. Like, what happens is oscillations, agents will continuously change their minds and run around aimlessly. A better idea is score point distance to the other enemy's intended position. This provides a stable solution and solves the decision oscillation. Is this just a complicated way to say that he will have a singleton that will kind of an enemy manager that will compute the scores? And then we have a priorities. Damn right we did. Lower priority enemies get out of the way of higher priority enemies. Here's how it looks. Red guy has a lower priority. Yeah, that's interesting. So you can imagine the stronger enemies pushing the others away, and the small one leaving place for the ones. And the priority, probably you can imagine many things. Priority based on health, based on ammo, based on, I don't know, energy, any kind of things. Some emergent order from using these really simple functions. Notice how the agent makes room for higher priority peers, the green guy that pops up. Up. Really nice. Really, really nice. This is great. Choosing the final result, step 3. So this is a final step and is a straightforward one. The simple approach is to simply choose the best scoring position, but there are some alternatives that include choosing a random sample in the top X percentage score. It is worth mentioning that you can implement decision inertia at this point. For example, keep using the same point if the score doesn't drop below a certain threshold, or only change if the score has dropped X percentage in the last Y timeframes. Very interesting. Caveats and opportunities. Caveats. Problems and opportunities. The scoring method described is very powerful and straightforward, but it can be hard to debug when dealing with lots of scoring stages. Yeah, makes sense. Why? Because non-linearities get added up and form non-intuitive results. A way to mitigate this is to keep stages stacks small and swap between them based on the situation. Let's talk about performance later. It's unoptimized. And it currently runs fine. Yeah, it runs fine on my machine. But that's not to say that it couldn't cause problems in the future. Let's look at some numbers. Say we have 10 enemies, agent on screen, and 2 players. 90 points. We're looking at 10 times 2 times 90 nav mesh queries. Yeah. Nav mesh queries. If you see nav mesh query, you should definitely panic. Generally speaking, spreading out computation across frames is a good approach. I talked about that in the other video. You can check it out. No, not here. There. Spreading work across different videos is a good thing to do. And depending on your game, maybe you don't need every enemy to always choose a position. Like, depending on your game, having so many dots for possible position might be already too much. Maybe you just need less than that. Maybe some enemies already stay a bit more far away. They are ready to jump in to take the place of another one that is injured. Maybe some enemies are also ranged enemies, and their decision process doesn't need to be as active as melee enemies. I always come back to this article. It is not the first time I see it, because it's just, I think, a great way to visualize and understand that, yeah, positioning enemies around your player is not something you should do just by using the nav mesh and say, oh, go to the player, go hit him. You get really simple behavior with this. With a method like that, you step up your game and you can create very interesting enemy behaviors with a kind of a simple solution. Now, if you combine this with other AI methods, let's say finite state machine or a bit more fancy behavior trees, then of course, the game starts to be more complex. But if you keep each piece quite small, the combination of all those small pieces makes for really great and interesting enemies. Perfect. If you reach this point, I never want to see you ever making a game where enemies merge into a fat mess of triangles. Now you know how to make it look good. At least in theory. Like and subscribe, and I'll see you next time.